Okay, so now we're back for our last example. And so let's again have a function where we have f of x equals the matrix A times x. And we're going to have A now be 2 minus 2 minus 1 and 1. And so, again, we can see that f is mapping from R2 into R2 because it's a 2 by 2 matrix. And by the way, as another aside, let's suppose that A was m by n. So if A was an m by n matrix, then if it was m rows by n columns, then it would be multiplying by n vectors, by vectors that have n components. So this would be n, and the result would be a vector with m components, that would be m. So even for non-square matrices that are m by n, we know we'll be mapping then from Rn to Rm in general. And of course, if it's square, n by n, then it'll be from Rn to Rn, here from R2 to R2. Let's take this off. Don't really need it now. Okay, so let's see. Well, let's again do the same thing we did last time. Let's put our domain down here. x1, x2, and we can start with, this is 1. Let's say this is 1, 0. And so that's that point there. Maybe I'll use colors again, so maybe I should reserve that for a different color. Before we do that, let's draw our target space. I have the tendency to make the axis here go a little not perfectly vertical, so let's see if I can do a little better with that than that. That one was pretty bad, so that looks better. And so let's say this is the target space. I'll again call it y1 and y2 as the components. And so f, I'll often write things like this. I didn't do it in the first example, but I'll do it here. F takes things from here and maps them over to here. And so again, let's ask the same question we asked up front on the first example here, and that is, what is the range of f? In particular, let's ask, is f onto all of R2? Is the what's f of R2? What's the range? Well, first question is it all of R2? And so let's look again at the determinant. And as I already indicated, we have an example where the determinant is 0. At least it better be 0 if this is supposed to do what I want it to do. 2, 2, so it's 2 minus 2, 0. Therefore, A inverse doesn't exist. It is not the case that for any y over here, there is a unique A inverse times y, x over here. So I can't write x equals A inverse of y. So x equals A inverse of y. Can't do it because there is no inverse matrix. So that's not going to work. So that tells me right off that the function is not on to all of R2. It's going to be mapping to some subset of R2, and we want to figure out what subset. I still need to, I've answered the question that it's not all of R2, it's some proper subset, but we need to figure out what subset. So let's go back to figure that out. Let's go back and do the same kind of thing we did in the previous example. In fact, I'll try to use the same colors to the extent that I can here. Let's let this be the first vector we look at, and then let's look at the vector 0, 1. And we will also look at the vector 1, 1. So we're going to be looking again at the unit square. In fact, let's even draw the unit square in here right up front right now. And of course, this is the 0 vector, the origin. And so we, of course, know right away that this is f of the 0 vector, as it always is going to be for matrix-defined functions. Let's see what happens to the vector 1, 0. Well, just like last time, the image of 1, 0 vector is going to be the first column here, which is 2 minus 2. So let's say that is about here. So that's f of 1, 0, which is 2 and minus 2. So let's say this is now 2, so that would be 1. And this would about be minus 1. And this is minus 2, and that's minus 1 there. Don't really have room to put it in there because of this, but, well, maybe I should put it in there. Maybe I should put in here that that's minus 1 because we're going to actually use that. Okay, so let's now look at the image under F of this vector, 0, 1, and that's going to be the second column of A. So that's going to be, and I guess I didn't write in here, that this is 1. I don't know if we're going to need 2, but we'll put it in there. So this is f of 0, 1, and f, and of course here's f of the origin, the 0 vector, and of course f of 1, 1. 1, 1 is the sum of these two, and it's easy to show that therefore always the image of the vector 1, 1 will be the sum of the two images, which is going to be, this is 2 minus 2, minus 1, 1. That's going to be here at 1 minus 1. It's supposed to be 1 minus 1. Sorry, that is 1 minus 1, but it's not f of 1 minus 1. That was a mistake, so let's actually fix that. That turns out to maybe not be as easy as as it sounds. So let's again say this is y1 over here, and let's say this is actually f of 1, 1. I kind of messed that up. This is f of 1, 1. And so the image of the unit square now is this set here. That's it. I'm going to call that the set D, even though it's no longer actually a diamond, because it corresponds to the D that I had in the first example, and that is f of s. So let's do it down here. F of s, the unit square, is this set D, but it doesn't look like that sort of diamond-shaped parallelogram that we had in the first diagram, in the first example. It's now that parallelogram has been squished down to a line segment. And so what would be the image of other points in the space? Well, the image of the x1 axis, I won't draw it like we did the first time, but the image of the x1 axis is everything from the origin all the way out here on this line. It's multiples of f of 1, 0, which you can just barely see there now. And the image of the x2 axis is going to be everything on this line also. I should have said if I had the whole x1 axis, it would be the whole line. The non-negative part of the x1 axis gets mapped to here. The negative part of the x1 axis gets mapped to here. The positive part of the x2 axis gets mapped to here, multiples of F0, 1. And the negative part of the x2 axis down here gets mapped to here. And that means that everything in the space is getting mapped into this line here. I'm going to call this line L. So f of R2 is this line L. It's nothing like what we saw in the first example, and that's entirely because in the first example, the determinant was non-zero, so we had a non-singular matrix defining f, which was therefore a one-to-one and onto function, a one-to-one correspondence. And here, by contrast, the determinant is zero. We have a singular matrix. The function f is no longer onto or one-to-one. It's clearly no longer onto. It only maps onto this, not to the rest of the space, okay? And we're going to see in a moment that it's not one-to-one. So far, we've seen 4 points, and they got mapped to different points. So that doesn't contradict the possibility that it would be one-to-one. But you can kind of see that it really isn't going to be one-to-one. In particular, you can see that because the whole unit square got mapped into this line segment here. And in fact, I think I will take off now some of what we put on here. I'm going to focus just on the unit square, and I'm going to focus just on its image, which is this set that I called D. I'm going to leave that L down there. I might want to come back and use that. So let's come back and say, let's just focus on the set D, this line segment here, which is the image of the unit square. So what I want to do now, and this is really the last thing we're going to do, I really didn't do that. I didn't do this in the first example, and that is I want to look at the pre-image. So let's come over here and look at the notion of the pre-image of a set. The pre-image of a set V is the set of all the things in the domain that map into V. And so in the first example, if I had a singleton set, a single vector over here in the target space, then its pre-image was just A inverse of that vector, or the set consisting of that vector, singleton set. So I maybe should have spent a few moments to point that out then, that in the one-to-one case, where I had a non-singular matrix defining the function, that the pre-image of a point or a singleton set over here would be a singleton set over here. Y over here, x equals A inverse of y over here. So the pre-image of there, it's kind of clean. That's one-to-one also, the kind of the inverse function. And so here, let's look at the pre-image of, let's look at the pre-image of the origin. So the pre-image of the set, because notice the pre-image definition says it's the pre-image of a set V in the target space. And of course, the pre-image is itself a set in the domain. That's what the definition says. So I want to look at the pre-image of the singleton set consisting of just the zero vector, the origin. And so what's that going to look like? Well, the pre-image of the zero vector is going to be, and here I'll write this, I'll keep this with this green color. That's going to be this line in the domain. Everything on that line, all the way out, all the way out. This is the pre-image of the zero vector. And it's actually, you can see that this is 1, 1, of course. So this is the set of all x's in here, such that x2 equals 2x1, looks like, if I haven't made a mistake. And so, in fact, I should be able to plug in here and say that if I have a vector x1 and 2x1, then I'll have 2x1 and minus 2x1, so that'll be 0, and I'll have minus 2 times x1 and 1 times 2x1 plus, no, indeed it's the case that if I put any vector in here that has an x1 and then down here is 2x1, x2 is 2x1, if I put such a vector in here multiplied by a, I'll get the origin, I'll get 0, 0. So this is correct. This is the preimage of this one point. So everything on this line gets mapped by this function into one point. So it's anything but one-to-one. We call functions that are not one-to-one, we say they're many-to-one, just meaning many could be just more than one point gets mapped to the same thing over here. This is many, many, many to one, if you like. Lots of things get mapped to that one point, f of 0. Let's see what is the preimage of, let's take the preimage of 1, 1. That, as you can check for yourself, is going to be this line. That's supposed to go through 1, 1. I didn't do a very good job of that. That should have gone through the point 1, 1 there. So this is f inverse of 1, 1 of f inverse of, actually it's 1 minus 1. That's f inverse of 1 minus 1. And in fact, I should write it as a set. So to be a little more careful here, I should write this as, just as I did up here, f, the preimage. I say f inverse because we're used to using this notation as the inverse function. I'm going to come back and say something about that in a moment. Let's just call this y bar. This is f inverse of the singleton set consisting of just y bar. And so, as I just mentioned, this notation is actually somewhat ambiguous. We use the same notation for two ideas that are very, very closely tied, very closely related. We use the notation for the preimage of a set, which is itself a set, because the preimage of this singleton set is this set here. So we use this notation to tell us the preimage of something, but we also use exactly the same notation for the inverse function when the inverse function exists. So in our first example, let me note, in the first example, we would have f inverse of a y equals a inverse y, and we would have some x would be this. And this was in the prior example, just to point out that here we're using this notation, the same notation as for the preimage, here and here. We're using this notation here for the inverse function. And as you can see that they're very closely related and tied together, but they're not the same concepts, but the same notations being used. So that can be a little confusing. And in effect, it kind of confused me a little bit because I wrote f inverse of a single vector, and that doesn't exist because the inverse function here does not exist. So that was an incorrect thing to write when I wrote f inverse of y bar, because the inverse function doesn't exist. F inverse of the set consisting of y bar, the singleton set, that's okay, it's the preimage. It's not the inverse, even though I keep saying f inverse, okay? So let's just close this off by saying, finally, let's look at this set here. Now, I've drawn this arrow coming down. That's supposed to go to the whole line segment. Let's say this set here is, I'll call it V, to square with the V that I've used over here, where I take the preimage. So this little set here is V. the preimage of V is everything in here. So here you can see that the way the function behaves when I have a singular matrix that defines the function is quite different from the way it behaves when I have a one-to-one correspondence, because the matrix is non-singular with a non-zero determinant. Here, things get collapsed. So this entire green line here maps to the origin, the zero vector. The entire line gets collapsed to this. The blue line maps to that point right there. The entire line gets collapsed to a point. This whole strip with a real width to it gets mapped into this little line segment down here. Things get squashed, collapsed, when we have a function defined by a singular matrix. I don't think there is anything else that I need to say about this example. So this means that we've pretty much done a kind of sequence of examples that, taken together, give us, I think, a pretty good idea about how these ideas over here work. And in particular, I want to note that these last two examples where we had, in both cases, a function going from R2 to R2 defined by a 2-by-2 matrix, one non-singular, this one singular, that what we did in these two examples is something that is very useful, that you'll find useful to do as we go forward, where to find out what a function like this is actually doing, to look at what happens to unit vectors, to the unit square, and see what that does in the target space. So I think that's a pretty complete story here for our examples. So that's it for today, and we'll see you next time.